Hey everyone, Mrs. Basega here, and today we're taking a look at Unit 6. As you've heard me say before, I want you to try all these problems out first. Then check the answer key. Especially check them out against the objectives on the side here. If you figure out which things you are struggling in, then you can narrow down your study to make sure you're focusing on the things you need to. All right? So we're going to skip the first two pages of objectives and equations. Let's do this thing. So it turns out that Benjamin Franklin is the person who named charges positive and negative. What happened was, as he was doing his experiments, he did experiments with silk and glass. And because those were considered like high class expensive objects, he called the charge on a glass rod positive because of its perceived value. He knew that the charges were different from each other, but he called them positive and negative for that reason. Inside the atoms of the glass, there's more protons than neutrons, and that makes the glass rod positive. Now, these two things had to rub together. This is called charging by friction. And during charging by friction, the glass and the silk rub together. So electrons leave the glass and accumulate in the silk. The silk has its own little protons, so that's fair, but because it gained electrons, it will be negatively charged. Someone asked me, why do electrons flow from one object to another during charging by friction? And that's because electrons are the lighter particle, they're easier to move, but moreover, between glass and silk, the silk has what's called an electron affinity. The silk just wants electrons more, and it's an innate chemical property of the silk. So before the materials were rubbed together, the net charge was neutral. The starting point of charging by friction is to start with two neutral insulators. But after the silk gets rubbed together, well, that's when they change charge. If the rod became positive, then the silk became negative. Because the silk has gained electrons, it must have a negative charge. But both are going to have equal magnitudes of charge. Because think of it like this, as the charges are being transferred, the positive rod lost electrons. So it became positive. So let's say its charge is 1, 2, 3, 4, 5. Let's say its charge is plus 5. Well, that means the silk must have gained 5 electrons. Its charge is minus 5. So they have equal magnitude because magnitude refers to the absolute value of the charge. So let's do our first calculation. The net charge on the glass is 3.2 nanocoulombs. Okay. We want the number of excess protons. So that's N. On our equation sheet, what relates Q and N? Q equals N times E. That's the charge Q, the 3.2 times 10 to the negative ninth. That's our nanocoulombs. We're solving for N, and E is the elementary charge. It's the charge on every proton and the charge on every electron. So to get N by itself, I'm going to divide by the elementary charge. So N can be calculated by dividing by the elementary charge. And I'm just going to round to 1.6 because that makes my life easy. In a calculator, make sure you put parentheses around the bottom term here. If you're using Desmos, it will do it for you. But if you don't put the parentheses around the bottom in a regular calculator, you're going to end up with a fraction of the number you want. This should give you 2 times 10 to the 10th protons. Notice that I should have some very large number. It should have a large number of charges. If n is some number less than 1, it probably means you forgot those parentheses in your calculator. Ben Franklin has this positively charged rod. He charges it positive by rubbing it with silk, and he calls it positive because glass and silk are both expensive objects. He then takes this charged rod, which is now positively charged, and it gets brought near a metal sphere. It doesn't touch. No conduction occurs. No friction occurs. So the sphere is still neutral. And in my head, I'm imagining the protons stay still, and the electrons are going to flow to the left. The electrons want to go left because that's where the other protons are. And because electrons are free to dissociate from their atoms when it's a conductor, those electrons have moved to the left side of the sphere. The sphere is neutral, yet polarized. It's polarized because no charges were transferred, like they were moving to one side of the sphere, but they didn't literally leave the sphere and move into the rod. So, staying within electrostatics and charging. Remember, electron affinity is just which material gains electrons, which likes the electrons more. So when PVC and fleece are rubbed together, the PVC rod becomes negative. So the rod must have a greater affinity. It becomes negatively charged, so it likes electrons more. So the negatively charged rod is allowed to touch the conducting sphere. Well, guys, this means it is conduction. When conduction occurs, the electrons still move to the far side of the sphere because they're repelled by the rod. But when this actually touches, the electrons in the rod are free to also flow into the sphere. And of course, they're going to want to do this because electrons want to spread out. They are repelled by all the other electrons in the rod. So let's imagine that these two electrons in the rod flow in to this side of the sphere. The electrons are going to spread into the sphere because think of the sphere as having excess space. The electrons are trying to expand or repel from each other into the neutral conductor. So I'm going to say the electrons move from the rod to sphere. And they move that way because the electrons in the rod repel each other. And since there's an opening to the right, they move to the right. Now, pretend the rod isn't there. Notice that this conduction has added additional electrons to the sphere. The sphere is now negatively charged. If it helps, another way you can picture this is picture that when these two objects are touched together, they're going to share some of the negative charge. So if this started with a charge of -9 and 0, well, conduction occurs, and maybe after the new charge is something like -6, -3, charges will transfer from one to the other so that they're both negative. If they're equal-sized objects, they have to evenly split the charge, but in this case, the sphere maybe looks a little bit bigger. So I don't know, maybe the sphere will have more charge. Maybe the sphere will have a -7, leaving just a -3 on the rod, right? Something like that. So what happens to the magnitude of the charge on the rod after it touches the sphere? Its charge has decreased. Because let's say I go back to the original numbers I used. Let's say if it was 9, 0 to start. Let's say after it transfers, there's 7 and -2. The charge on the rod has become less negative. The magnitude of the charge has decreased. All right, let's do another one. So this is charging electrostatics again. A negatively charged PVC rod is brought near, but does not touch. And then a student comes by and pokes the back of the sphere for some reason. We know the electrons stay still, and we know that the electrons in the sphere want to move to the right. But this time, the person is at ground. This lets the electrons flow out. They're going to flow all the way out to the ground, leaving, well, no pictured electrons in the sphere. I would say the electrons flow from the sphere to ground. They move in this direction because they're repelled by the rod. When the electrons in the sphere are repelled by the rod, they take any path possible to get away from the rod, including into the ground. Now, let's say the person moves their hand away and the rod goes away. Well, that has taken the excess electrons with it. So we would say the sphere is positively charged now. Okay, electrostatics also deals with insulators. In fact, I want you to take a close look at this picture for a moment. Remember that both insulators and conductors can become polarized, but an insulator has to make sure that the electrons don't fully dissociate from their little proton buddies. The electrons form strong bonds at the nuclei, so they can't just leave and flow somewhere else. They're going to stay within the atom, they're just going to flow to the side. So the wall right now is a polarized insulator. So let's start from the beginning. The negative balloon comes by. It repels the wall's electrons to the right. So my electron flow would be to the right. This makes the insulating wall polarized, which looks fundamentally different than it does for a conductor where the electrons fully dissociate. But this still leaves more positive charge on one side than the other. So right here, the negative balloon is close, very close to the positive portion of the wall. This causes more attraction than the far side does repulsion. Polarized objects cause attraction. So I'd probably say the most important parts are that it causes polarization of the insulator. That leaves the positive side of the wall next to the negative balloon. And polarization causes attraction. You can cause attraction whether something is neutral and polarized, like in the previous example, or maybe it's positive. You actually can't tell. So obviously, if the ball was positive, you'd be like, all right, opposites attract, it has to be positive. But it could also just be that the sphere is polarized with its electrons flowing to the left. That leaves positive charges on the sphere close to the negative charges of the balloon, causing the dominant attractive force. So one more time, it could go neutral and polarized always causes attraction. Or it could be just simply positive and opposites attract. Same thing with C. Um, this is going to be polarized causes attraction. The protons in the can stay still, so let's draw those stationary. Oh, it kind of looks like a face. Still kind of looks like a face. The electrons in the can are free to move through the conductor, and they flow away from the balloon. That means the can becomes polarized. And when it's polarized, it always leaves the side that's positive closest to the negative. The dominant interaction is going to be attractive. So again, polarized causes attraction. Now, why this doesn't work on the aluminum supports for the whiteboards? My whiteboard is surrounded by metal, but that metal touches the wall, which touches the floor. This doesn't work so well for conductors, especially if the conductors are grounded. And I don't mean they're in trouble. What I mean is when the electrons are going to flow around this whiteboard, well, electrons are going to be able to flow in and out. It's going to actually start to take some of the electrons via conduction. And these electrons are going to be able to flow out through the conductor to the ground. It's actually going to start taking the excess charge off the balloon. So I guess we could explain this two ways. There's conduction, because the balloon is touching a conductor. But when that conductor attains some of the balloon's charges, excess charges, those excess charges flow into the ground, neutralizing the balloon. So it doesn't work as well. Coulomb's law is the force between two charged objects. So Q's are my charges, K is our universal constant, and R is the distance between the two spheres. If the distance between the two spheres becomes 4 times larger, imagine I'm putting in 4 for R. If I put in a 4 for R, I would get 1/16 of the original force. This is called proportions. So let's say I take the next one. One charge is doubled, so let's say Q1 becomes twice as big, and Q2 becomes 3 times as big. K's and R's stay the same. So this is like getting 6 times larger than the original. Finally, let's say that a bunch of things happen. So two charged objects are brought near each other. The charge on one of them doubles, the charge on the other triples, and the distance quadruples. The new force is 6/16 times the original. So because 1/16 was less than 1, this means there's less force than the original. Because 6 is greater than 1, this is going to be more force than the original. And 6/16 is less than 1, so this is less force than the original. So let's actually calculate this force. If I had to do our K, Q1, Q2, one skill that might help might be to start figuring out what number goes with what. Point 2 is going to be the R. The charges are 3 times 10 to the negative 6th and 9 times 10 to the negative 6th. And I'm being a little sloppy, like I dropped the 3, the negative sign on the 3, but that's because I know that I'm absolute valuing these. I don't actually need to take into account positive or negative because those are just referring to the direction of the force, which we already know. If this charge is negative and that charge is positive, then these attract because opposites attract. This means each force is going to experience a force along the radial axis towards each other of equal size, equal magnitude, and opposite direction, just like Newton's third law for some reason. The universal constant for gravity is electricity is 9 times 10 to the ninth. It's a pretty sizable value, and that's why the forces can be so big, even though the charges are super small. So the electric force is 6.075 newtons towards each other. But hey, I said they're equal in size and opposite in magnitude. Or sorry, equal in magnitude, opposite in direction. There we go. So if that's the force on Q1, this is automatically also the force on Q2. They attract each other. So if Q1 is being attracted to the right and Q2 is being attracted to the left, they're part of the same interaction, so they experience the same magnitude of force. One way you can think about it if you want is like if you really wanted for H, you could calculate the force of Q1 on Q2 by switching Q1 and Q2 in this equation. But notice how that doesn't matter at all. If you switch two numbers in the order when you multiply, you get the same number. So for that reason, and Newton's third law, they experience equal magnitude forces. All right, so let's get some field lines here. Electric field lines have to point away from positive charges and towards negative charges. So I would fix the first one by drawing this arrow down and this arrow left. So notice that they had 2 out of 4 of those arrows in the correct direction. That student would not get the direction point. This student would get the shape point because it shows repelling, leaving that empty space in the middle, showing that they're repelling, so that's good. It's showing field lines pointing away from positive charges, that's good. It's taking up a majority of space in the box. That's good. But our lines can't cross. And the reason lines don't cross is, remember, this represents the direction of a force. The direction a particle might start moving if it was placed there. And if it was right here and the lines were crossing, that particle would be moving in two directions at once, which it just can't do, so lines don't cross. Finally, in this one, they have the shape for attraction. For a dipole or attraction, you would get field lines that point away from positive and towards negative, but you'd be able to tell they attract because they're kind of pulling towards each other, right? This person should be showing repel, not attract. So they have the right shape if one were positive and one were negative, but that's not the case you have, so too bad. Would they get the other points? Yes, they drew field lines that took up most of the space. The field lines don't cross. They'd get 2 out of 4 points. They wouldn't get the direction point correct because this part right here shows lines going towards a positive instead of away. And they don't get the shape point. So you should be able to draw the field lines for a single positive or a single negative. In either case, imagine they're kind of vectors that fill up the whole space. Nice straight lines because there's only that one charge here. Lines point away from positive or towards negative. Be able to draw the field for single charges. Be able to draw for attracting, like a dipole, or repelling. In fact, if we put some little numbers on here, you have to be able to draw a single positive, a single negative, attracting, repelling, and capacitors. Those are the shapes, folks, so we can get those. With a capacitor, it's going to draw straight lines from positive to negative. You can draw the end effects if you want, which are the little curves on the outside. But note that with inside the capacitor, I should have nice equally spaced lines indicating a uniform field. Since field maps point away from positive charges, Q2 must be positive and Q1 must be negative. Q1 is negative because field lines point towards it. The field lines can also help us figure out which charge has more magnitude. Let's count them up. Around A, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think that's 16. So A has 16 field lines, and D has 1, 2, 3, 4. Oh, maybe I didn't need to count them. Q1 has the larger magnitude because it has more field lines. Now, let me erase some of my notes on here so we can see our points better. Electrical field strength is indicated by how close or how dense the lines are. So let's draw a few equally shaped boxes. Around C, around A, I'm just trying to get the size approximately the same. Around D, whichever line has, or whichever box has the most dense field lines will have the greatest, highest, most strongest electric field. So that would be A, because it has, I don't know, 6, 8, however many lines going through it. Then D, because it has 1, 2, 3, maybe 4 lines going through it. Then C, then B. We can get this by density of field lines. The more field lines closer together, the more electric field strength there is. Now, in this case, the electric field is pointing down, away from the positive plate and towards the negative plate. So I've labeled the positive and negative plate, knowing the electric field pointed away from positive towards negative, and it's going to have some nice equally spaced arrows in there. Because of this positive and negative arrangement, the electron is going to experience a force up. It wants to go towards the positive charge. Electrons travel in the direction opposite the field lines. So if the field lines were going down, away from positive and towards negative, then the electron should be going up because it wants to go towards the positive charges. Now, to calculate the magnitude of force acting on an electron, I could go try and do the Coulomb's law equation, the KQ1 business, but this is only good if I have spheres of charge. So instead, use Fe is equal to QE. Because this is a single electron, its charge is 1.6 times 10 to the negative 19th coulombs. And again, I'm being sloppy, knowing that, yeah, there's a negative sign there, but you can absolute value this. And you can absolute value this because you already know that the electron's going up. You know its direction, so you don't need that negative sign. Now the electric field, E, is 32,000 newtons per coulomb. 32,000. And just do some unit analysis here. There's 1.6 times 10 to the negative 19th coulombs. If each coulomb of charge has 32,000 newtons each, well, then I'm going to be left with newtons at the end. This gives me a force of 5.13 times 10 to the negative 15th newtons. And maybe your calculator is reading 5.13 e negative 15, but remember, those are the same numbers. It's just we don't want to write out the 0.0000 blah. Now, I will say that D, and I will tell you during class, but I'm going to tell you again right now, is using an equation that you and I don't have to do. So skip it. You do need that number, though, to solve for E, so I will give you this number in class. It's basically that if you know the electric field and the distance between the two plates, you can calculate the potential difference. You can calculate the voltage. So if there's 32,000 volts per meter and they're 4 centimeters apart, that's 0.04 meters, I can multiply to solve for V. Between the top plate and the bottom plate, there's 1,280 volts. So the electrical potential of the electron, you can kind of picture it like this. The top plate is going to have some positive potential. The bottom plate is going to have some negative potential. But the potential difference between the top and the bottom has to be 1,280 volts. So splitting it up, knowing that the central potential is 0, that means the top plate has positive 640 volts. The bottom plate has negative 640, and then all the increments in between. So maybe there's a 320 in here and a negative 320. Nice equally spaced equipotential lines, as they're so called. So when I go calculate the electrical potential energy of the electron, I'm using the potential difference between the electron's current position and where it wants to go, the positive plate. So I'm getting the potential difference from here to here. That's my delta V. So it's not the whole 1,280 volts because it doesn't go across the whole space. It only goes through half the space. So let's calculate this out. The electric potential energy is Q, that's the charge of the electron, times delta V, the difference in potential between its current position and where it wants to head out. The charge of an electron is the elementary charge. That's the 1.602 times 10 to the negative 19th. Again, being sloppy here because I know that I can just absolute value this. And for the delta V, the electron starts at 0 volts and it ends at 640. So final minus initial. Delta V is really taking the difference between where you started, its initial potential, and where you ended, the final potential. So the electrical potential energy is 640. This is 1.024 times 10 to the negative 16th joules. Later, when we get into the light unit, we'll talk about a special unit of energy that's even smaller than a joule. Because we talked about how, like, joules are really tiny. When I eat a meal, I'm probably eating millions of joules of energy. But there's a special unit of energy called an electron volt that we use when it's really small amounts of energy, like this 10 to the negative 16th joules. Small. Now, at point A, it's at the middle of the plate. This is where it has all this electrical potential energy. But at point B, when it finally hits the positively charged plate, all of that's going to turn to kinetic. Guys, this is the only, not free body diagram, this is the only energy bar chart you're going to have to know how to do. I'm not going to give you weird middling ones where it'll be like half and half. It's all and all. So all potential, all to all kinetic. Now, the electron is the thing that's going to have the kinetic energy when it moves. And the capacitor plates are the things that create that electric field. So the two items in the system that exchange energy are the electron and the capacitor. So all of the potential energy, that 1 times 10 to the negative 16th joules, turns to kinetic. And as you know, to find the velocity, I'm going to use my kinetic energy equation. So there's 1.024 times 10 to the 16th joules, or negative 16th joules. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. That is on your equation sheet. Just look it up, guys. And I've got to solve for phi. So I'm going to end up dividing this whole term to the left. When I divide that whole term to the left, I get 2.24 times 10 to the positive 14th equals v squared. I'm not done yet though, because I want v by itself and I still have v squared. That's also good because 10 to the positive 14th as a speed would be faster than the speed of light, and we're not breaking physics here. So square root both sides. That gets rid of the square on the right-hand side, and this gets us a nice reasonable speed of 1,000 of 14,993,595 meters per second. Your calculator might give you all these digits, but I don't super care about all those digits. I'm going to take my first three knowing that like I knew this many significant figures. So let's call that 1.50 times 10 to the 8th meters per second. It's approximately half the speed of light. Now, humans can't get to that speed, but we can make particles get to that speed. Basically, the mass of the electron is so small that its velocity and acceleration can be very big. So expect small energies with big speeds. With a uniform electric field, you end up with a positive potential near the positive plate and a negative potential near the negative plate. So if I want a proton to have the highest possible electrical potential energy, I want it to be as unstable as possible. So picture I'm holding a proton at point A using a pulley system. A would be the most unstable place. The electric potential energy is highest where it is most repelled. Because think if I let it go at A, it would speed up, speed up, speed up, and end up at the negative plate going really fast. So it has high potential at A. If it was at E, then it's practically on the ground. It has almost no potential. But an electron is the opposite, right? Because an electron is most repelled in a different position. The electron is most repelled at E, It really wants to go to the positive plate. So someone would have to be like pushing it down and holding it in this unstable position where it does not want to be. The electron wants to like attract to this positive plate, speed up, speed up, speed up, and then speed off into the distance. The electron has the most potential energy where it's most repelled. So let's get electrical potential energy again. Electrical potential energy is charge of the electron, or proton, times the change in potential. And it's the potential difference between its initial position, so that was 200, and its final position, negative 300. It didn't it didn't go all the way through this plate, right? It didn't go from 300 to negative 300. It started at A. So I'm putting in the charge of the proton. So that's 1.6 times 10 to the negative 19th. And my final minus initial, so remember it's always final minus initial potential. The final potential was negative 300. The initial potential was positive 200. So 300 minus 200, that'll give me negative 500 because it's like negative subtracting a negative, it's becoming more negative. This gets me 8 times 10 to the negative 17th joules. Again, expect small energies and expect big velocities. Since all the energy went from potential to kinetic, well, I have, by conservation of energy, the same amount of kinetic energy as I do potential energy. It's all or nothing, guys. In this case, it's going all potential to all kinetic. And just like on the last page, we're going to use that to calculate a velocity. So I'm taking my 1/2 mv squared. I get a point for the equation. K is 8 times 10 to the negative 17th. This time I'm putting in mass of a proton. A proton is a little bit more massive than the electron. It's actually a lot more massive than the electron. I don't know why I said it was a little bit. It's about 10,000 times more massive, and therefore, when I do this out, I'm expecting a slower speed for a proton. So just like before, we're going to divide by this half mass to the left. This gets me 9.588 times 10 to the 10th equals v squared. And I'm not done yet because I need to square root both sides. I don't have v by itself, so I'm going to square root both sides, and this gets me a much more reasonable speed. So it's not greater than the speed of light, it's 309,529 meters per second, so much slower than the speed of light. And if I want to use scientific notation, that's 3.1, 3.10 times 10 to the 1, 2, 3, 4 to the 1, 2, 3, 4, 5. Much slower than the speed of light, which is 3 times 10 to the 8th. Now at F, it's saying, okay, imagine that we move the electrons and protons. They're not starting at A and E. They're both right in the middle. If they're both right in the middle, then they have the same PEEL. Because think about it, they have the same Q, they have the same charge, and they'd have the same delta V. Their potential difference would be equal to each other. Whether a proton is started at C and moves to the negative plate, or an electron is started at C and moves to the positive plate, they both go through a potential difference whose magnitude is 300. So Q is the same because it's absolute value, so it's 1.6 times 10 to the negative 19th. The delta V is the same because it's both 300. They have the same PEL. However, they will have different speeds because they have different masses. The proton has more mass and therefore will have less velocity You can kind of think of this in terms of conservation of energy. They're going to have the same kinetic energy, but the proton has more mass, so it will have less left over to turn into velocity. You could also think about this in terms of Newton's second law. Newton's second law says that acceleration is caused by net force acting on a mass. But the inverse relationship between mass and acceleration means that if mass gets bigger, you're dividing by a bigger number, making acceleration decrease. Either way you think about it, mass is going to make the proton slower, either acceleration or velocity, than the electron. And that's all, folks. So hopefully I was able to help you answer some of your questions. Best of luck.